Thank you very much, Stan. It's a pleasure to be here and to tell you about recent work I've been doing, thinking about emergence of gravity, and in particular the way that may influence our thinking about dark matter and dark energy. Gravity works very well, as described by Newton's law even, or Einstein's theory in solar system, bending of light. It has been spectacularly confirmed recently with the existence of gravitational waves. And so there are many tests that we like to preserve when we think about emergent gravity. So it's not like we're going to change any of this, except we're going to think about gravity in a different way from a more microscopic perspective. Indeed, there are many questions about gravity that we still don't fully understand, actually about our universe. If we think about our universe and we look at the energy content of the universe, we see that 96% of the universe is not understood and has to be in some form of dark energy, with 70%, and what most people believe to be dark matter, 25%. And it's true that when you assume that Einstein's equations are correct, then there's no other way to conclude anything other than there must be some additional matter. If we look at clusters of galaxies where we have strong lensing data or weak lensing data, indicating there is additional gravitational force other than what's due to the visible matter. And also in galaxies, when we study their rotation curves, we see that they don't obey the Newtonian law, which would tell them to fall off if we only include the visible matter or the known matter that's there. So we have to assume that there is something like a dark matter force that increases the gravitational attraction. Or is there another way if the laws of gravity are different? Well, the reason that most people don't believe this to be true is that there doesn't seem to be a conceptual reason why gravity would work differently in this context. That, I think, is about to change when we think about gravity in a different way, in particular about gravity as an emergent force. There's actually some experimental or observational indications even for that. If you look at these rotation curves, they start to deviate from the Newtonian law. So if we put in only the visible or baryonic matter, we get the usual Newtonian law that would dictate the velocities to fall off with a certain way with the distance. But what is observed is that it flattens out, and therefore we need to add some additional component to make, up for this difference. Now, empirically, it turns out that this point where sort of the deviation starts to occur from the Newtonian law always appears when the acceleration has falls below a certain value, which we can express in terms of the Hubble parameter, the present day Hubble parameter, for some magical reason in this kind of equation. Now, that's very difficult to understand from just the particle dark matter point of view. I mean, this seems some magic between the acceleration of the universe and a galaxy in the universe is very tiny, so why would it know about it? If I think about the universe as purely having dark energy in it, then we have a cosmological horizon, and you can sort of represent it as follows. If I look at the Hubble parameter, it tells you how velocity depends on distance, and there must be some distance where this velocity becomes the speed of light, and that I call the cosmological horizon. So there's some horizon we have in our universe if you think about it as filled with dark energy. And I mentioned this because there's a similarity between this horizon and the horizons of black holes. So let me go to black holes, because as theoretical physicists and string theorists, we have been studying black holes for years, and we have learned quite a bit, and actually the indications that gravity is emergent comes from studying black hole physics. And there are some famous formulas due to Bekenstein and Hawking having to do with the entropy of a black hole. When you study their quantum properties, you find that black holes emit radiation with a famous formula computed by Hawking, which expresses the temperature in terms of the gravitational acceleration at the horizon and the entropy given by the area of the horizon. And then there is an equation very similar to the first law of thermodynamics that tells you the relationship between the change in the mass or energy and the change in this entropy, and then you recognize precisely with this equation that you have the usual first law with the temperature out here. Now, in cosmology we can do a similar thing, as I said, because the cosmological horizon also has similar properties. You can actually calculate in de Sitter space, which is the space with only dark energy, that there is this cosmological horizon. Therefore, there is also an entropy and a temperature that is determined by the Hubble parameter. Now, the equation I showed you that tells us when we see the deviations from dark matter appearing can be nicely expressed in these two quantities. So when I write down the temperature in this quantity, so I left out Boltzmann's constant if you want to be totally precise about it. But if I take this as an energy scale and I divide the energy of the mass in the system, and I divide that by the temperature, and I compare that to the entropy, sort of the Bekenstein-Hawking entropy associated with the radius where I'm at, then this relationship, which I noted before, is exactly equal to this relationship. So there is some relationship that seems to use the same quantities that we calculate from black hole thermodynamics, or actually horizon thermodynamics, and the amount of energy that we sort of can associate with a certain mass. So this equation is the same. And so why is this happening? There's actually a reason, and this comes from thinking about gravity in a different way. And this has been going on for some years, that using string theory and black hole physics, we seem to conclude, indeed, that gravity is emergent. And that means that we can derive it from a more microscopic perspective, just like the equations of elasticity are emergent because we can derive it from a more microscopic perspective. Actually, let me demonstrate one thing for you. I have here some elastic material, which if I bounce it, it really bounces very high. It's a little ball, and I can calculate what it does by using the theory of elasticity. The reason I'm going to demonstrate this is that, first of all, it bounces like, oh, now it bounces, now that goes. Anyway, it bounces quite well. People have seen it here. But I can put it on the table and wait for a very long time. The theory that describes the elasticity in this material cannot be applied to what happens at very long time scales. Namely, when I put it here and I leave it there, it will flow. And so there is a difference between how a system reacts at short time scales and long time scales. I'm going to say the same thing in our universe. The space-time reacts at short time scales as we can describe it with Einstein gravity. At long time scales, something else will happen. And this comes from indeed thinking about gravity in an emergent way. Now, I'm not the only one saying that gravity emerges, and actually not from quantum information. There's a whole group of people here in the Netherlands, but also in other countries, that are saying the same thing. Here I picked something from a website. It's It from Qubit. It's a group of scientists in the US that worked on, and it says, well, the major developments in our understanding of quantum gravity indicate that, well, there's a deep connection between gravity and quantum information theory. And actually here, one of the last programs in the form that was awarded last year, actually it started just this month, is our program, and our program leader Erik Verlinde here indeed says quantum information theory gives a new boost to understanding quantum gravitation, and maybe we understand space-time and forces very differently. Now, what is this quantum information, and how does it sort of appear in the theory of gravity? Well, quantum information, then you have to think about qubits, so that's spins up or down, or 0 and 1, where you can make linear combinations. And you can do a very nice thing with quantum information, namely entangle it. This is what Einstein, Podolsky, and Rosen already taught us. And here's an example of an entangled state. And if you think about a qubit as having all kinds of possible choices, namely not just 0 and 1, but all the possible phases I can put in here, it's like a two-sphere, then you can see a connection that is sort of the entanglement. Now, this is the way we should think about the entropy of black holes. And indeed, there is a slogan now which is called ER is EPR. So EPR was Einstein, Podolsky, and Rosen. They have these pairs of entangled qubits. And Einstein and Rosen actually also noted that black holes have this bridge that connects, or a wormhole that connects two sort of different universes. And they're connected by an area that is sort of precisely the area of the horizon. And actually now we interpret this connection in terms of entanglement. Namely, entanglement entropy is precisely the Bekenstein-Hawking formula, And you can think about the area basically as being defined by the number of qubits that are being entangled in both directions. So entanglement entropy basically counts how many of those pairs we have in making the vacuum. And actually locally in this looks like the vacuum. So this is not just a statement about black holes, it's a statement about space-time. Now that other picture I showed you on our proposal, which is this one, actually comes also from this EPR ER idea. Namely, physical black holes, we don't have the other side of the horizon, we only have one side, because then we form a black hole by collapsing matter. And this is the picture indicating then that the entanglement is not with the other side of the horizon, or the other side, this other universe. It's really with particles that have been emitted by Hawking radiation. And actually what we learn from this is that with physical horizons, we don't have just entanglement in this local area region across this neck or here. You have actually long-range entanglement, and basically that corresponds to a thermalization of what's happening in the neighborhood of this horizon. Now we're going to apply the same thing later to cosmology, and actually it's going to change the way we think about it. But let me first go to a situation where this has been studied very well, which is a space that string theorists love, namely anti-de Sitter space. It's a space that not like our universe because it has no dark energy in it. It has a negative cosmological constant. And basically it's like the ground state. And there it satisfies the entanglement entropy can be seen, defined also for the vacuum, as I said. And we do this by splitting the space into two parts and ask how much entanglement is there. And then there's just a way of counting how many lines are we sort of cutting across. Actually, I forgot to say that this picture here is actually one of those pictures that people are using this framework, which is called the tensor network, where you can think about these dots as being units of quantum information that are being entangled with each other along these lines. So if I then start cutting these lines, I count how many lines I cut, and that tells me what is the entanglement entropy, and that grows like the area. So this is exactly the area law that we know, and this happens to be true in anti-de Sitter space. Why is this important? From this area law we can derive, and this has been done, the Einstein's equations. At least at linear level, we know that the Einstein's equations need this area law. And this is something that has been shown quite recently by a number of authors and believed to be true generally. We can derive the Einstein equations just like we derive the equations of thermodynamics, and this is why gravity is emergent. But it's emergent only, the Einstein's equations only emerge if we assume this area law. Now I'm going to change to de Sitter space, and there is a very easy way sort of how we can do this in the metric. Namely, anti-de Sitter space is the metric with a plus sign, and this has this boundary which we use sort of in ADS CFT sort of to do a holography. So we have some boundary description. In the Sitter space we don't have a boundary, we have this cosmological horizon. So this is the space-time picture, so time goes up, and there is some line that we call the cosmological horizon, and there's no asymptotic boundary, so there's no way we can do the same story with entanglement. How am I doing with time? Okay. So what is the difference between these two spaces? And for this I have to tell something that is very familiar to condensed matter physicists. If you have area law, it means basically you're in a ground state where entanglement is short range. That means you have indeed entanglement between nearest neighbors, and then I cut this region and I compute the entanglement between inside and outside, and you see how many lines I cut, that's the area. However, if there long range entanglement, that means there is entanglement between these nodes and very far away ones, and I start cutting this, then I cut all these lines for all the nodes inside, and that grows like the volume. This happens when you have thermalization, and you can actually have an entropy density in that case. And it's even possible that you have both. So there you have an area law and a volume law. And this, I claim, is the situation actually in de Sitter space, and this comes from this idea of EPR ER. So here I go back to my horizon picture, and this is the horizon of our, well actually the galaxy I wanted to be sort of more in the middle, but this is the entropy, and then this is the temperatures and the scale. And there's again some entanglement picture, which is long range entanglement that gives you an entropy density. And this is my hypothesis. I call it now a hypothesis, but I believe when we understand microscopically how to describe de Sitter space, we will learn this. that there's an entropy density which is associated to the positive dark energy. So there's a difference between this anti-de Sitter space and de Sitter space because de Sitter space has a positive dark energy, and it actually leads to a volume law contribution. And we can calculate this by the following rule. The volume law should be such that when I put the radius r equal to the radius L, that it gives me exactly the entropy of the total horizon. And this determines uniquely what is the entropy density. Now I'm going to derive this relation that I see in data. So I'm going to show to you why the gravity actually starts deviating from Einstein gravity because of this volume term. So I'm going to calculate how much entropy does matter take away from this de Sitter space. And that's a very nice calculation that basically amounts to putting the mass in the center and ask what happens to the horizon. The horizon actually becomes smaller, and therefore it reduces the amount of entropy associated to the dark energy. So it's like it takes away a little bit of the dark energy volume. And you can calculate this number, and it's precisely the change in entropy of the horizon is equal to the energy associated to the mass divided by the de Sitter temperature. So it's this object that I see in the data. And this change in the area is exactly the area I saw also in the data. But however, here I calculate it as a change of the area of the horizon. Now I want to know what happens inside, and for that I need to sort of change this calculation to something that happens in the interior. In particular, I want to know how much entropy is being removed locally. This I can derive from the Einstein's equations locally by checking the change in area, which is sort of like the change in entanglement entropy. It's sort of a standard calculation. Actually, it's one that was already noted by Feynman, that in general relativity, when you compute how the area depends on the distance, so I compute the geodesic distance from the center, and I ask how much does it increase with distance, then when you put a mass there, actually there's a slight area deficit. And you can calculate this deficit. It's again a formula very much like I had before, but now it has, instead of the mass times, actually what you find is actually proportional to the mass, in the sense that the mass is basically causing this area to be smaller. Actually, in 2 + 1 dimensions is very well known. It's sort of a conical deficit. This is already analog of that in a higher dimension. But again, I find some change in entropy, and this I now compare to the entropy I associated with the dark energy. So this is what explains why there is this deviation, namely the amount of entropy that the matter takes away, which is this number. If I compare it to the amount of entropy that's available in the dark energy, it's precisely when this number becomes smaller than that, that this starts happening. So this is where the volume contribution starts entering, and we get a different effect. So this is basically the general idea, and I'm going to finish pretty soon because I actually have only some calculation to do where I, instead of changing the area, which is happening by Einstein gravity, I'm changing the volume. And so the idea is that Newton's law actually is derived from the area law of entanglement. As I mentioned, this already has been done basically. This fails, however, at cosmological scales, and that is where the volume contribution starts entering. And there changes the nature of gravity. It actually becomes an analogy of elasticity, because I'm removing a certain amount of volume. I can calculate the amount of volume that I removed basically because it has a elastic response. I mean, I know how much entropy I have, I know what the entropy density is, I know how much is being removed, and so I can calculate how much volume is removed. And then there's a nice law that tells you that the displacement of the medium basically can be obtained by this standard equation, namely it tells you that the displacement here times the area integrated is precisely the volume that's being removed. And then there's just a standard calculation in elasticity, and I have to do indeed some calculation of forces. The main equation I need is actually some equation on the strain, and there I get a relationship that I'm going to compare to the data. I have to skip some steps because of time. That's the same one actually, sorry. Yes, the equation I'm going to get is this relationship. It's a relationship between the amount of entropy that has been removed, as I said, but actually it's a relationship with the effective gravitational attraction that's sort of due to some apparent dark matter. So there's no real dark matter, but I'm going to calculate an additional force and representing it as if there's some dark matter. So this would give me then a relationship between how much matter I would see and how much matter I'm missing. And this relationship is quite a well-known relationship and recently got a lot of attention. It's called the mass discrepancy acceleration relation. Actually, this is the name given by Navarro et al. It's appeared actually in a paper by Lilly, McCoff, and Schombert. Actually, McCoff has been writing many papers on this. And it's sort of a familiar variant of what's called the baryonic Tully-Fisher relation. And here it is. This is a relationship between the acceleration that would be due to the baryons. I'm thinking here, yes. This is the baryons, and this is the acceleration that's being observed. So if there would be no dark matter, that would be just a straight line. But this is the deviation. But the fact that it satisfies some specific relation tells you that the amount of baryonic matter and dark matter are very much correlated. And this is quite a magical thing if you think about dark matter as a particle. What this relation also connects to is a phenomenological description due to Milgram. I call it Mond phenomenology. It's not a theory. It's just some formulas that work and seem to fit the data without any free parameters, basically. And this amount of data follows also from the formula that I derived. Now this is all, if you look at the distances within, say, 10 to maybe 30 kiloparsec, or maybe, well, a little further down on. There's a very nice test recently that has been done that tested the same relation much further out using not strong lensing, which is sort of bending of light. Weak lensing has to do with distortions. And you can do this with galaxy and galaxy. So you have a galaxy in the foreground, so somewhere here, another galaxy in the back, and you calculate what the deformation is sort of in the shape of these, and you can calculate what is the gravitational field. That gives these relations. This was done by Margot Brouwer and Manus Visser joined the team as well, and a bunch of other astronomers that did the survey of many galaxies, about 10,000 of them. And then they calculated the effective field as a function of the distance. And this radial distance goes much further out, basically 3 decades up to a megaparsec, and you find the same relationship. So what actually you see here is the relationship that I get from the equations. That's the blue line. That has no free parameters. These are 4 different bins where the height every time changes, and it seems to, you can actually put the data together in one plot, where you get this sort of as the expectation. They're scattered, but that has to do with the uncertainty, or actually the errors in the measurements. But the fit, of course, you can also make with the particle dark matter profiles. But there you have a free parameter, namely you can basically adjust the height of this. So they do equally well, but you have to indeed realize I have no free parameter here. This is just theory. I calculate one formula, and this comes out in a range of data that has not been tested before. I can show you many other plots, but I think I'm over time. I can, a few minutes, then I'm going to show you a little more of this. So this indeed, as I said, is a test, a new test actually with weak lensing data. There can also be tests you can do with clusters, and these are a little more tricky. Here is the amount of matter that you need to have to explain the observations. This is the amount of matter that Mond would still need to explain the same thing. It's slightly less, but this is what's seen in gas, and there's a gap in here. Of course, there's also stars in here, which he didn't include, but he was simply making the point there was no way of correcting this. Here what I did is, using the equations I have, I calculated indeed the gas I put in, the stars I put in, and I calculated what would be outcome. This would be the outcome of my acceleration using the formulas, and this is what Mond would require. So I basically reproduced a very similar plot as this one, where I indeed make clear that I can get this kind of amount of dark matter from just assuming these components, while Mond needs a lot more. Actually, the equations I used here are written down here. I just showed them very briefly. This is the same relationship I had before, except I replaced it by an average matter density for baryons and by sort of apparent dark matter. And the same formula can be rewritten now in a equation that looks like this, and I don't know why the equations drop off. But it also tells us something quite interesting, namely if you take this to be the average baryonic density and dark matter density, you can ask how this depends on the radius, and particularly you can take the radius to be the radius of the universe, where this product would be equal to 1. There's a concept here which has to do with slope, how these things are behaving, and I get an equation for the abundance of baryonic in dark matter. So these formulas work very well for clusters. Actually, here's another example, but I'm going to show you just to finish. The same calculation also does this for the omegas. And this is the data. Sorry, these are the data. This is the relationship I have. There I would like to stop.